to the cloud.
That would be delightful.
Okay, I think we're functional. I got the recording. Then Mike actually asked to go through some parts of the homework, so I'll do that.
Are you able to hear me, Dr. Beaucage?
Let's see, I'm here. So anyway, yeah, the undergrad guys, who's the undergrad people? Oh,
There's one.
okay, all right. Anyway, so what's your name?
I'm Jonathan.
Oh, Jonathan, okay. Because it's Robert that asked about, I don't know, he said something, but anyway, so whatever you guys want to do, it's okay, you know. Yeah, I think it's okay too. You guys are doing really well, actually. Like, I don't have any problem with how you're doing. So I don't know, if you wanted to do the other thing, it's like more undergrad based, and there's that book.
I did download the book to look at it, but.
Yeah, it's a pretty good book. Like, Fried's a good guy. He left here, he became head of chemical engineering at Louisville. He published a few books, and I don't know, he's a good guy. So the book's pretty good. I just have never used it in a class, but if I did teach a class, those undergrad polymer and chemical engineering, I'd use that book, because it's just exactly what you need to know.
Yeah, that's good.
So, but we're trying to do a, they don't call it a minor, they call it a thrust or something in polymers. Like if you have a,
It's not a minor, but a focus kind of.
well, maybe they call it a focus. That's probably a good name for it. Let's use that. Steal ideas now. It's like, anyway, yeah, they can't call it a minor because there's no major. If you don't have a major, you can't have, no, because there's a minor in materials, right?
Okay.
Anyway, there's some reason they can't call it a minor, but they want to have some polymer, something in chemical, you know, so.
The way they did it at my undergrad, it was basically like, you're all chemical engineers, but you kind of focus on specific subset, right? So like some people have more environmental kind of engineering classes, some people have more.
What did they call it?
It was like a specialty. I think they called it, was the title they gave it. But basically, it was like you all take the core engineering classes, you know, operations, mastering, you transfer all that.
Yeah. Where was this?
Miami University.
Oh, Miami. Okay.
But then
Oh, yeah. All right. Miami,
other than that, you focus on other stuff. So you have paper, bio, biomedical.
Yeah, actually, we got the same things.
Yeah, you just take what you want to actually eventually go into.
Yeah. We kind of got the same thing going on, I guess. So that's pretty weird, huh? That thing's like in the way. Should I fix that? All right, so yeah, he said, Mike, you there? I think people can't talk.
I don't think I can. I don't think I can talk.
Maybe it's because I don't have the speaker turned on or something. Let's see. Put the speaker up. Mike, can you say something?
Hello?
No, doesn't work. Anyway, that's a limitation of Zoom, I guess. Anyway, I think he said A and C, so I can go through. This is the wrong thing. I can do that one, but so it's just like, what's tacticity, you know? I don't know why he said this one. Everyone seemed to get that one.
He was wondering about the last part, the optimal number of mergers
Oh,
to consider.
Okay, well, that's an important question. Like, so you get in this tacticity number and it's for triads. But I think I said that in class, but basically, if you're going to crystallize, so the crystal's going to be so the crystal is going to be 100 angstrom, kind of about thick. The idea is something like that. So each of these units is 2.5 angstrom, like a carbon-carbon. So if your persistence is 6.7 for polyethylene angstrom. So I don't know how many that is. It's like 20 units, right? So if you're going to do an odd number, you'd want 21. So I don't know what that even be called. It's like triad, pentad, up to 21. So that's kind of what you need to know. That's kind of answer A. And it forms that in polypropylene, it's gonna have a helix that makes that crystal, right? So again, it's probably gonna be helices of 21 units or more that you want to know about, which isn't possible. You can't measure that. So you can take what you can do is take and there's papers on this, you can take the triad tacticity. So 2 R groups, triad, I think, maybe 3 R groups, I guess. And then you can make a computer program about how the thing was polymerized, and then you can simulate up to 21, like figure out how it fits together. Like what are the odds of getting it to crystallize? Otherwise, so these numbers are kind of just a hunch then, they aren't really anything of any use particularly. Because you can get up to heptads and nonads, like 9. And then they want to get, I think they can get 11 dodecads or something. And then after that, they don't have a name for it, I think. Or quintacads or something is 15. Anyway, so they do that with NMR, you can measure it. So anyway, you want to know, like, does it form a helix or not? The answer is it helps if it's got 90% isotactic triad. That helps, but it doesn't prove that it does, So there's a long answer to that last part. Isn't that simple? Right. So the other thing is that so if you say atactic, so then you have to use this triangle thing, right? So it's 1, 2, 2. How does it go? It goes 1, 1 for dyads, and then 1, 2, 1 for iso symbio hetero. Then the next one would be like 1, 3, 3, 1. And it goes like 1, 4, 6, 4, 1. This is pentads. This is heptads. Right. So and this would be random, right? If you want to say random equals atactic, then you could say that. And you could keep going, right? But you never would get to like random because you can't measure the entire chain. Being random, it's not possible to do it. So atactic doesn't really have a firm meaning. So it's important to point that out because people say it's an atactic polymer, but it could be, what they mean is it doesn't crystallize. Like the symbio hetero and iso will crystallize, but this one won't crystallize. So the only real meaning to atactic is it doesn't crystallize. All right, you could say, well, like a random distribution, but basically atactic means like a physical behavior of the thing, it doesn't have to do with like this tacticity exactly. People will throw the word around loosely, put it that way. So it's not necessarily like a firm thing. Anyway, you probably couldn't figure that out. Maybe you could. I mean, it's a possibility you could, and I'd give you a lot of extra points or something. But basically, I'm just saying that, Anyway, then I think he said C, yeah, C. So C is this equation. So
Mike is texting in the Zoom chat too. He sent me a
Oh.
message.
Yeah, but see, I'd have to be watching Zoom to see that. It's like all these urgent messages. The building's on fire. Nuclear bomb went off in New York City. So, all right. I'm more interested in a deeper physical explanation. Oh, that's a lot of words, Mike. How come I can't hear you?
Oh, if you
Trying to talk.
you go to the little speaker icon, like the little microphone icon,
Here?
where you're talking
Are you there?
Yeah.
on Zoom.
Get a free-
To the very,
Oh, yeah, I remember this. Set a speaker. Extron media port.
one of those was like out here, like
How about same as system? Here, say something, Mike. Nope, can't hear you.
He's still muted.
Oh,
I don't think he tried to speak.
oh, Oops, unmute and say something. I command you. I have such power, you know, it's like, now how do I get rid of it? What did I do? Here, there. All right. If you talk, maybe we'll hear you someday. He has a dog, you know, it's a adoption dog, but it's deaf and blind.
Oh, he does?
Yeah, there's like some disease or something that dogs can get or something like that. I forget what it is, but this, anyway, this is like a organization that does this stuff, but anyway, maybe he has the sound off because of that. Okay, so let me just go back here. I'm not even coherent. So the question is like that equation, right? This equation 3 or something where he, this thing, like that number 1, I guess. Expand it, right? So I can give you the, it's described in this Binder paper, you know, if you want to read it, but it's kind of a long paper and it goes into stuff we haven't talked about yet. So, but the philosophy, a lot of the, and he derives the, this two times the persistence length is the bond length, wherever that is. He derives that a different way than the way it's conventionally done in here. He doesn't explicitly say it, I guess, somewhere. Right, so persistence is 2 times the bond length, that thing. So anyway, he derives it a different way. So it's kind of interesting using this average cosine thing. And he does an expansion of the cosine, an algebraic expansion when it's small, and then he uses that to get the same argument, you know. So that's kind of interesting. Anyway, for this business though, I mean, what I did, so you have like the persistence length. So it's like LP is this vector for the K step of the
You gotta
chain.
change the.
Oh, sorry, thanks. I should put tie a string here. Then the absolute value dot this R for the whole chain. And the average of that over all Ks, all chain. Like average of all chain. So you're taking your step along and you get to this point where you have like RK. It's a K unit. And then the overall chain has this vector R for it. It's end-to-end distance. That's also, these are both vectors. You can dot product the two and you get the angle between the two. So kind of like that angle, and then cosine of that angle. So if that angle's, say the thing is a rod, like case 1, a rod. Right. So that means that angle is always 0, right? And cosine of that is always 1. That means that your persistence length is R. It's just going to be R because this thing first is a unit vector, so it's got unit of 1, and then it's normalized by itself, so it's actually a value of 1, even if it isn't a unit vector. Right. So then your whole chain is a persistence length. So that kind of works out. 2, if it's random, so say theta is always random, then the average of this that costs, then this cost thing becomes 0 in that case. Because the average, because cosine is symmetric above 0. So this part cancels that part, so it's 0. So that means that in that case, if it's random, then the persistence is 0. So that's good. That's kind of what you want. So that checks out too. So that, and then you can say in between, like it's going to have some value in between. So you have like 0 random rod R, and then in between it's going to have some continuous behavior. Well, that's going to be how your persistence length behaves. With this, how rigid it is.
Is there Sorry, is there a true zero? I mean, even you were saying the atactic polymer is just, it doesn't crystallize. But that's not a zero in persistence length, right? Or is it?
Well, that's a good question. I mean, in this equation, yes, there is. And there is also, if you do like R dot R, there's a zero. Like it's possible to have it completely random. But the Kuhn length can't be zero. Right? Like the Kuhn length can't be zero because you said it's like the steps of a random walk. So it's like out of value. If that goes to zero, then the chain, the whole thing falls apart. Right? So yeah, there's a difference between these two, philosophical difference.
Okay.
So this thing can be zero if you have totally random. There's more than that. There's more problems than that. Okay, like if you take polystyrene, put it into gasoline, then that makes napalm. That's what they sprayed in Vietnam, burned the kids with. Also, they're still using it too. You know, if they used it in Iraq, and I think some other people have been using it, but it's pretty easy to make. You know, you can spray it. So anyway, that chain isn't going to be a random walk when you do that. It's going to have this expanded coil. So you have this 3 states. You have like a collapsed chain, then you have the Gaussian chain where it can cross itself. Then you have this expanded coil where it doesn't cross itself. Right? So this is called a grid solvent. That's called a theta solvent. This is collapsed. So we'll talk about this in the next section. But basically, the only one where any of this stuff makes any sense is the theta condition, which is the polymer melt. Like when it's in a melt, these interactions disappear and it becomes like that state. So this works in a melt, but if you put anything in a solution, it's not true. So chain in solution, you can't say LP, true LP is LK, because you don't have LK, because LK is based on this random walk function. LK is NL squared is R squared. Right? So these are all kind of philosophical things no one pays any attention to. Also, that this thing only applies when it gets to an infinite chain. That's another limitation of it. Right? So no one pays any attention to that at all. They just run right over those things. So anyway, there's some twist to this thing. Nonetheless, you can measure it. So let's see. I don't know. Did I answer that, Mike? Since I can't hear you.
Yeah.
I can hear you. I can
Oh,
hear you.
you can really?
Yeah. It's just like you're here.
Oh, okay.
Like live,
Yeah, so unfortunately, right when you started explaining it, I dropped out. I don't know why. So I guess I'll just have to go re-listen to the replay of it.
All right.
And as far as the first one goes, I was more looking at, I had explained this to Josh, as far as the triads. So we had put triads for the answer, and my thought was, at least from the commercial perspective, when we run NMR on our polymers, that's what we care about, because knowing the percentages of the triads is enough to give you the macroscopic properties of the system. If you know the frequency in which the different triads appear, you can make assumptions on which one's going to be the dominant one, and then what properties are you going to get because of that dominant triad or the couple triads that are present. So that's why I kind of was asking that question, because I know maybe from an academic perspective, the more MER units you can know, the more you can understand micro or nanoscopically what is really going on for the chain itself, each individual chain. But from a macro level, the triads seem to give you enough information to be able to predict properties of the polymers.
Yeah, I go with that. I mean, it's good enough, right? So you just take it. I mean, that's fine.
Yeah. Okay.
Thing is, like, you got to realize at some point that will fall apart,
Yeah.
So it's good to know that isn't really true,
Mhm.
I mean, there's a lot of things we take for granted and we just kind of go on living, right? But
Yep.
at some point your brakes are going to fail and you'll hit the truck, So that's kind of how it goes.
Okay.
But memory lane. But anyways, the other one, okay. I mean, this.
Yeah. I think that was fine. It was more about trying to understand the physical meaning of how the theta plays into everything, and why the N groups tend down to go to a persistence length of 0, and it just seems like you get more of a random distribution of the conformations of your N groups compared to the internal of the chain, where you're more likely to be in an extended state or closer to an extended state and not able to reach those random conformations.
Yeah, I mean, we're looking for that dot product, and it just, you can work out from the dot product that it's that.
Yeah.
Bender says it's done in Florey's second book. He derives that equation. I didn't actually derive, but this dot product to get R squared,
Right.
kind of the origin of it. So I guess Florey in his second book, he drives that, and then he also says that the Yamakawa, there's a book by a Japanese guy, Yamakawa. It's on the webpage, but I didn't bother looking at it.
Okay.
That where he derives that thing too, I guess.
All
The
right.
Yamakawa book was pretty thick, and then he gave it out for free. It's kind of funny. It's not at the bottom here somewhere. Like somewhere here it says Yamakawa. I think it's in here somewhere.
That's okay. I think the explanations, they got me what I needed.
There's one in here somewhere. It says one. Where?
It's right at the bottom, very, very bottom. of that.
Oh, yeah. It says books here, I guess. Kyoto is like the Japanese, first it's like, it was an imperial capital of Japan for a while in the 1500s or something. That became like the Zen Buddhist center. So there's like more monasteries. And Kyoto University is like the, I don't know, it's kind of like the Cambridge of Japan, I guess. And then, but really, like, it's got this prestige, but actually, University of Tokyo is like got all the money now. So it's like, in Tokyo is this huge city. So this is like a little town on a mountainside or something. Anyway, he was there, I guess. So a lot of the Polymer people were at Kyoto. It's like, all right. So anyway, that's that business. Then, all right. So I just want to move on today to polyelectrolytes. Through this thing. So these are important for battery membranes because you have like vinylidene fluoride and then PEO are weak polyelectrolytes that they use to make if you want to make a solid. All right, so it's in here somewhere. So if you want to make a solid electrolyte. So right now you have like, what do you have? You have a graphite. Oops, sorry. You have a graphite electrode and you have a lithium oxide electrode. And then you have an electrolyte that's like fluorinated something. It's like some kind of R group and then fluorine, right? Which is these fluorinated hydrocarbons. They're the things that blow up in the battery. So because it's highly flammable, and also when this stuff burns, it makes like HF, which is like it's not the most acidic thing, but it dissolves your bones inside out. So one drop will dissolve all your bones, you turn into jello and die. And if you put water on it, it makes it worse. So the only thing you can put on is calcium. It'll eat up the fluoride somehow. So you do this calcium gel. If you're working with HF, you need a calcium gel. Nice thing is it'll dissolve anything. So if you have a rock, you want to know like what's in the rock. So you want to do mass spec on a rock. So you can't do that. Mass spec means you gotta vaporize it and then make ions and send it through some kind of a machine. To separate the parts. I mean, HF will do that for any rock, like the silica, titania, any of your filler materials or polymers, and catalysts and things. So you put it into HF, put it in a thing called a bomb, Teflon bomb, and stick it in a microwave. You cook it for like an hour. And it liquefies anything. Then you take a small amount of that, inject it into this thing that vaporizes it, and you can figure out what was in the rock. So Anyway, this stuff is nasty. If you can avoid working with it at all costs, avoid it, you know? So, but batteries, all of your batteries have this potential to produce HF, like all lithium ion batteries. So, so in order to separate this from that, there's a polymer film here. That's usually like a porous polypropylene, actually, like IPP. It's just a thing to keep the two electrodes separated, because this is actually going to be like 1 micron separation distance. This thing, so there's not much space. You want to, if these two touch and it arcs and blows up. So anyway, that's one way polymers are used. The other way is that they're trying to get rid of this organic fluoride thing so it doesn't blow up. So you make the whole gap some conducting material. They need an ion conductor. So of those is polyelectrolytes. So sulfonated, you take polystyrene, another aromatic, and then you just sulfonate. I don't know. This is negative, and there's an H plus out here. This is SO3 minus H plus, right? So you take polystyrene and then you put sulfuric acid on it, and you can kind of get some of the aromatics to sulfonate, right? And then when you melt process that, it makes like these domains of this sulfate groups in it that make kind of channels through it. And nobody understands anything about that. They've been around since the 1970s, maybe earlier than that. So people have proposed like so many different structures for this that you could just spend a lot of time reading about these ionic pathways for this stuff, right? So anyway, this is a strongly charged polyelectrolyte. Another choice is you make this, well, they use also polyvinylidene fluoride, which is fluorine, is 2 fluorines on a polyethylene. That's a piezoelectric polymer. So you can make, it's actually the Atlantic base of the Atlantic Ocean, the North Atlantic is covered with this stuff. The Navy put it all over it so they can hear like any time, because it's piezoelectric, like it moves and makes electricity. So they're hooked up to like radios that send off a signal whenever a submarine goes by. So basically the bottom of the Atlantic Ocean and the Arctic is completely covered with PVF2, sheets, because the other inorganic piezoelectric, like in a microphone, like titania, barium titanate things, those things they're too expensive to cover the Atlantic Ocean with. This stuff is basically polyethylene. So you can put a lot of it out there. I think that the inorganics work better maybe, but this stuff's a lot cheaper. So anyway, that stuff's also used because it can also conduct ions through, because it's got these fluorine groups. And the other one is like this simple polymer, polyethylene oxide, right? So it's like this guy. So that's got no bonds here, but it's got this like polyethylene with an oxygen in it, an ether group, right? So basically that can also kind of form ion channels, I guess. The nice thing about this is PEO is soluble in water, so you don't like water process films with it. And then what people have done is they've doped this stuff with, so this is a weak polyelectrolyte. This is a strong polyelectrolyte. And I think this is also a strong polyelectrolyte. Right. So anyway, this is categorized into these different groupings. Right. This stuff actually phase separates. This is a single phase when it's in a melt. And then anyway, so what happens to this persistence of this thing when you stick on these charge groups? Well, so that's been studied a lot. Also, proteins are polyelectrolytes, and nucleic acids are polyelectrolytes. Basically, there's a lot of polyelectrolytes out there. And then there's a thing like you can take have a cationic polyelectrolyte and an anionic polyelectrolyte, like a sulfonated polystyrene, then something with an amine group on it. And then those two will kind of hook up, right? Because the plus and minus attract each other. Then that makes something called a coacervate, which is kind of like the origin of life. more or less. It's also any kind of goo. So if you're in the goo business, like Procter and Gamble, so these coacervates are really important to controlling what happens. And then in research, people are studying how you can make like kind of jellyfish functional devices. Like combine these things together to make like a self-propelled blob thing. People are doing crazy stuff, right? So this is one of them. So anyway, so there's a lot in polyelectrolytes. So it goes on and on and on, and they're not that well understood in the same sense that the synthetic polymers are pretty well understood. You know, in some ways, at least there's theories for it. So this thing becomes kind of complicated. So in the end, there's three sizes of importance. There's A, which is like where your charges are. They don't make a minus for like sulfonated polystyrene. You have some spacing of the things. There's the persistence length of the chain, like polystyrene persistence length would be like 10 angstrom, right? And then this A spacing might be like 5 angstroms between the carbons, like if each group was charged. And then there's the bi-screening length. And then there's also a thing called Beaucage length. Okay, so there's kind of like two sizes that have to do with charges. So if you think about, these two sizes are kind of important. So say you have a gun. And we can do this with a lot of different things, but guns are popular in the US. So say you shoot the gun and you're standing over here. So you duck and you run, right? It's like you're running away from the gun, right? So that means you're within the Debye length and within the Beaucage length. I can't spell Beaucage, but I'll show it to you after. Okay, so if you're a little bit further out and then you shoot the gun, then you just duck because you don't know where it is. Like, where is the gun? So it's maybe echoing all over, but you know there's a gun, so you ducked, right? And then there's a length where the Debye length, where you're surrounded by guns, so you're in some kind of bad situation, and there's guns going off all over the place, and you basically don't do anything because if you duck, there might be a guy shooting at you there, or if you jump or run, you're going to either run into it, you don't know, so it has no effect anymore. So this is called a screening length. So Debye invented that for bilayers. The original business of this is bilayers. And then this also is used here because so effectively beyond the Debye screening length, there's no charge. There's no charge beyond the Debye screening length. Like you can't see anything. There's no reaction to it because it doesn't matter. It's just constant gunfire. You get used to it. It's almost like you have that AC hum going on and like you just don't know it's there anymore. Right. So beyond the Debye screening length, you're in the AC hum region. And here it's called mean field. So you can't tell the direction. There's no direction, but you know something's going on. I'm talking about molecules. Like molecules know something's going on. So they'll change because of that condition, but basically they don't have a directionality to it. They're not going to run away from it or be attracted to it. And within the Beaucage length, you're attracted to it. So you can see how those concepts might be important to ions or ionic charges, you know, like and many other things, right? Not just this. So anyway, this screening length idea, particularly, so the idea of a mean field, this kind of directional field, or specific, it's like specific interactions. So those become like broad concepts overall, like the idea that because mean field is much easier to model, right? So you think about your enthalpy of interaction between two things, and you can describe it in terms of this Hildebrand del parameter. So it's del of A component, B component, and then squared times KT gives you, and this is like the cohesive energy the energy that holds something together divided by the volume. So cohesive energy density square root is del. So if the cohesive energy density of two things is the same, they tend to mix. So they have a low input P of interaction. And then if they're different, then this thing gets larger. Right. So that's a mean field. There's no actual direction to it. Right. So that equals this Horry-Huggins chi parameter, or it could also be the Hildebrand interaction parameter. So it's sometimes called omega, sometimes called some other things. So it's just like a mean field concept for how you talk about interactions. So you can just have like one number, that's the interactions. It doesn't have any direction. So the whole system becomes like T delta S and then delta H. Nothing here has any direction to it, and then you get the free energy of the system. Right? And the H is just some generic number. It's not a vector. It's not a, it doesn't have direction. Right. So that's the whole mean field concept, and that applies above the Beaucage length, but below the Debye screening length for charged systems. Right. And then specific interactions are quite different than that. Like you're going to get this thing about that they attract each other. So then you're starting to talk about like 612 potentials where you have R dependence and stuff to it and everything. So this is like a different realm. We're going to have to talk about organization of things. Because if you're going to make a crystal, it has to have direction. So you have to be in this region. If you're just talking about glasses, like disordered, then the mean field is good. So for many systems, you can use a mean field description to talk about them. And then for a lot of systems too, especially chart systems, you need to have these specific interactions. Okay, so that's kind of a mapping out of these two size scales. You have the Beaucage length you don't usually worry about. I mean, so there's basically these three size scales: A, charge spacing, the raw persistence length, and then this Debye length, which is also called lambda is 1 over the Debye length. Okay, so Debye, so let's just go to the PC there. All right, so this is the bilayer. This is the original model. It has nothing to do with polyelectrolytes. But you have a surface. This is like a piece of silica. So SiO2, the surface is covered with OH groups that are stuck to it. And those have a minus charge. So you have a minus charge and you put that into water, then this would be like, I guess, H plus would kind of organize around it. The idea is you have a bilayer. You have the charge on the surface and then this other layer that organizes. Okay, and if you're talking about entropy, like this other layer is really important because there's only one silica particle and there's a gazillion of these counter ions. So the entire entropy of the system is governed by that organization of that second layer, right? So that becomes like the most important thing to the whole thing. Then there's other effects that happen further out, right? This is in water. I think the blue things are water surrounding like ions in it. So Debye figured out that there's some point where like it doesn't matter anymore, right? Where you can't see anything. And the reason he said is because it's like the gun thing. This gun's all over the place. I don't know anything about any guns at all at that point. It's just the AC hum. It's like the background, right? So there's a Debye screening link somewhere here where things don't matter anymore. And he found out that, or he proposed that screening link was going to go to the square root, 1 over the square root of the concentration of counter ions that you put in. So if you have soap, which is a charged molecule, so soap is going to have like decade 12 carbons, which is like fat, right? So and then you put like an OH group on it for soap. So you put lye in. So you have wax is kind of like oil that's fat, right? And if you put it in lye, you can put OH on it, then it becomes charged. Then that can self-organize so that the dirt likes the fat and this likes water, so that you get micelles formed. OH on the surface, dirt in the middle. And it can solubilize things that aren't soluble and like carry them away. Oops, sorry. Thanks. So you have like dodecane, 12 carbons. It's polyethylene, like short polyethylene is wax. Then you put it into lye, you can get an OH on the end, right? So it's saponification. And then once you have that, this part likes dirt, that part likes water. The dirt part surrounds dirt, and the water part goes to the outside and it makes micelles. Right? So that works great because of the charge. Basically, there's a charge on this thing. So it's like negative all over the surface, and that's fitting into water. But if you put salt in, so it depends on the device screen like of the water. It's the other way around. Plus sides here. So there's a bilayer of this thing. So it's got like the charge on the surface. That's first layer. There's a water surrounding it that organizes around it, almost like a crystal, because it's so regular. And then, or like a polymer, like I talk about polywater. People have studied this extensively, right? This is called the hydrophobic effect. So kind of circa like 1980, I guess. And then polywater was kind of like 1990, maybe. So polywater became like, whatever, nanotubes, I guess, for about 3 years. So water can kind of line up into polymer chains, kind of, Anyway, so there's a long history to this kind of organization thing. There's people have written books just on this, like the thermodynamics of the hydrophobic effect, maybe like 10 books. So it's anyway, so whatever. So if you put the salt in, it's going to go with 1 over the square root of the concentration of the salt. Is going to be like how this Debye length goes. So the Debye length will get smaller and smaller the more salt you put in, until finally there's no charge anymore. So that's called salting out. Then the soap doesn't work anymore. Like you try to take a bath in saturated salt, it won't work. or try to take a bath in seawater, right? It won't do anything because the surfactant effect doesn't work anymore. So you call it salting out. You can salt out a protein, you can salt out soap. The other thing weird that happens that's incidental, not that any of this is incidental, but you start with these spherical to minimize the surface area. Then as you add more salt, these things start to become elliptical for some reason. And people have theorized about the reason. If you add more salt, they become like a polymer. So the micelles can become these long worm-like things. And then those can entangle. So you can get viscoelastic properties in these things. So if you take shampoo, and you look at the bubbles, like they used to have a Prel ad, they'd show the bubble in it is shaped like that, right? Like a teardrop, because it's a viscoelastic, it's a polymer. But there's no polymer in Prel at all, 0. It's all just these, what they call worm-like micelles, or they can also be called like hair micelles or something. There's a couple other words they use for it. But basically, they're polymers. They're almost like model polymers in a sense. So, so anyway, yeah, if you can saponify, you can just put OH, or you can put sulfuric acid in and make SO3 groups here, and then you get a detergent. So you have soap as OH, detergents are these other groups on the end. They could be cationic or anionic. So you can put an amine group on it or a sulfate group usually. You can put Zwitter ionic, which are switching between anionic and cationic. There's a couple other options, but basically anionic is a normal soap detergent that people use, you call shampoo or whatever. Anyway, so that's kind of part of this thing somehow. So anyway, not sure how I got onto that, but it's just as well. All right, so we got this stuff. So that's the bilayer. So then you talk, these things we don't care about because this has to do with actually like particles, right? So you have like the charges, fixed charges in the second layer, the stern plane, and then there's a layer of, so to go like plus minus, there's a layer that can't be sheared off, like when it flows. So that's a shear plane. Then there's this diffuse layer, right? So in bulk solution. So then that potential is described by this Debye equation. So it's actually this thing. So the potential between the charge on a chain and the counterion charge is going to be the charge squared divided by the dielectric constant, and it's 1 over r, so it's a decaying potential. Then it follows this exponential decay, right? So Debye proposed this. Everything Debye did was some exponential function. Like he liked the exponential function. He used it everywhere he could. This is probably one of the most famous ones, is Debye potential. Then the limiting factor is this Debye screening length, which I described, and depends on the square root. N is the concentration of the counterion. So 1 over the square root of counterion, and then Debye length gets smaller with a higher temperature because you're shaking things up more, so you can't. It's easier to get to the point where you can't sense the charges. And then that's it, I guess. Right? So it's 1 over the concentration square root is the main rule for this thing. So if you double your salt, you get half the Debye length. That's the idea of it. So anyway, so this is polyvinyl alcohol. That's another weak polyelectrolyte. I don't think it's not used. It crystallizes. They both, PEO also crystallizes. I don't know. I don't think it's used though for battery electrodes. This is for battery solid electrolytes. There aren't any. I mean, there are some commercial, but most of the batteries are these ionic ones. Yeah.
Sorry, can you go back for just, what is the epsilon there?
That's a dielectric
That's
constant.
just the dielectric, okay,
Yeah.
thank you.
So, yeah, it's just the number. It has to do with the media that the thing's in. So it's how the charges, communicate with each other differently in different media.
Okay.
So water, I think, is 85, and I don't know, vacuum, I guess, is 1. And then everything has a different dielectric constant for the media. So it's like the charges of the things. This is the stuff it's in. Anyway, so that's going to mitigate, like, so if you have two, say you put silica, which has a surface charge, and you put it into butadiene rubber or into PDMS, right? So the silica will organize because of that charge, like it will make weak correlations in butadiene rubber, but in PDMS it won't, because the dielectric constant is a lot smaller for PDMS, and then this number gets smaller, so it screens out the charges. So you can explain a lot of behavior of things with that equation. So it's important. It's one of the main, it's one of the main things that Debye came up with. He did a lot of things in polymers and also in colloids and things. So let's see. So that's how the Beaucage length behaves. And we don't really use the Beaucage length much. It's the Debye screening length is the main concept here. So the other thing that happens here is that the if you get to the right charge concentration, you can get this something called counterion condensation, which makes your polyelectrolyte not a polyelectrolyte anymore. So, and that's governed by this number U. There's this U number. So, and this has also to do with like random motion of. So this is the U number. So it's the it's a balance between the ions. The counter ions have translational entropy, like KTs moving around, right? So they have. Then they interact with this charged polyelectrolyte. So there's an enthalpy of interaction. So there's an energy of this randomness or entropy part, and there's an enthalpy part, and they balance out each other at when the free energy is like 0. Then this U parameter is governing that balance out. So it's got a KT term, it's got the charge term, and it's just the ratio of the enthalpy of interaction to this kind of randomization entropy. right? So you can get this number that decides, well, the counterions just cluster and all around this thing. And once they cluster there, then the device screen, because it's the concentration of counterion goes through the roof, and the device screen length goes to 0, and then there's no charge anymore because it's all screened. Right? There was just guns everywhere. Like it's just all, it's like a gun club meeting or whatever. Right? And then everywhere else there isn't any, right? So basically you can't run away from a gun show. It's like, it's like you might as well be anywhere else, but everyone's going to be shooting. It's like, so anyway, so that's the idea. This U number could decide, like, do you have counterion condensation or not? If it's less than 1, then entropy is favored, and you don't have counterion condensation if it's bigger than 1. So people talk about this U number in polyelectrolytes also. So I guess that's about it here. I have to reassess this. Oh, yeah. All right. So we're going to have, so you'll have like a, this is the final thing. So you have the persistence length of your chain is going to be your bare persistence length plus this added thing due to the charges. And that's got this functional K's, the K is 1 over the device screening length. Yeah, K to the -1 is a device screening length. Kappa, right? So this is a functional, it's just saying it's like a linear combination of the charge part and the, and that is the Bejerem length, so it is used here. But basically, the rigid, like polystyrene's 10 angstroms, and then add on for the sulfonate groups this term. So you just get a linear combination to get the persistence in a polyelectrolyte. And usually, like a protein, the persistence will be the whole chain. Like it's just rigid, unless you salt it out. So it's, you play games with the salt content, the counterion content to figure out how the thing's going to behave. Right. So why don't we quit there? So do something. So Friday, like if Armageddon hits or Snowmageddon hits, whatever, maybe can I let you guys know in the morning? We could just go online and do the class, I think, because there's no point in killing yourself. I don't know, if it looks like it's going to blow over, I'll come in, Well, all right, why don't we just plan on doing it online, doing it on Zoom? And then if it looks like for some reason it's going to be okay, I'll send out a message and say, like, we'll just do it. And then I'll still have it on Zoom anyway, so you can do it that way too. All right, okay, so see you.